All right, so today we're going to do Chapter 6, Section 8, Graphing Radical Functions. So get your graph paper ready. We're graphing. Our learning objective is to graph square root and other radical functions. A square root function is the inverse of a quadratic function that has a restricted domain. A horizontal line can intersect the graph of f of x equals x squared in 2 points, where f of negative 2 is equal to f of 2, for example. Thus, so that they're talking about like this. Thus, a vertical line can intersect the graph of the inverse in 2 points. So f inverse is not a function because it fails the vertical line test. So when you have the inverse, here's your regular quadratic. When you have the inverse of the quadratic is not a function. But we can restrict the domain so that the inverse of f, so that the inverse of the restricted function is a function. So if we say if f of x is equal to x squared and we're just dealing with x greater than or equal to 0, then the inverse is a function. Inverses of the power functions y equal x to the n, with domains restricted as needed, form parent functions y equals q nth root of x for families of radical functions. In particular, f of x equals square root of x is the parent for the family of square root functions. Members of this family have the general form. So I need you to get your highlighter out. I need you to, we're definitely going to highlight this parent function, and we're going to put stars, sparkles, whatever we need to do so that we see the parent function is f of x equals a square root x minus h plus k. All right, so here's our key concept. If we have a parent function, either a square root or a radical, an nth root, if I reflect it across the x-axis, I am going to put the negative reflection in x-axis. So I'm going to put the negative out in front of my entire function. Negative in front of my function is a reflection in the x-axis. If I'm going to stretch it, my a value, my coefficient out in front is going to be greater than 1. If I'm going to shrink it, my a value is in between 0 and 1. If I'm going to translate it horizontally, that's my h value here. That tells me if I have x plus 4, that means a translation 4 units to the left. But the translations act the same way on a root function as they do a regular function that we've studied. And then a vertical translation by k, plus k moves it up k, minus k moves it down. Okay, so let's take a look at a couple of square root functions. What are the graphs of square root of x plus 2? So this is our parent function. I'm just going to put the parent function in red. So a square root function, square root of 0 is 0, square root of 1 is 1, square root of 2 is 1.4, square root of 3 is 1.7, square root of 4 is 2. So I get a nice little rainbow shape. So this is my parent. Go ahead and label that parent. Any square root function is going to be a nice little half rainbow shape. If I'm going square root of x plus 2, it's going to be the same parent function, but translated 2 units up. So instead of being at 0, 0, I'm going to be at 0 plus 2. Instead of being at 1, 1, I'm going to be at 1, 4. Instead of being at 4, 2, so this one is y equals square root of x plus 2. All right, square root of x minus 3. So instead of being at 0, 0, we're going to move everything down 3 units. 1, 2, 3. So instead of being at 0, 0, we're at 0, negative 3. We're at 1, negative 2, and 4, negative 1. So same graph, translated down 3. Now we're going to do a couple of horizontal shifts. Please note, the vertical shifts are outside the root. Horizontal shifts are inside the root, and they go opposite of whatever sign is inside the root. So let me put my parent function down. We'll put him in red again. So here's our parent function. And our y equals square root of x minus 3 inside the root is a horizontal shift 3 units to the right. So I'm going to start here at 0, 0 and count 1, 2, 3 units to the right. And so that's y equals square root x minus 3. Then I'm going to have y equals square root of x plus 2. So that's a horizontal shift of 2 units to the left. Back 2 units. And it shifted it to the left. Okay, so now we're going to add the vertical stretch in. So let's throw down our parent function. So here's our parent in red. This guy says we're going to do a horizontal shift of minus 2, a vertical stretch of 3, and a vertical shift down 4. So if I shift my origin point, I'm going to, instead of being at 0, 0, I'm going to be 2 units to the left and 4 units down. So 2 units to the left and 4 units down. Normally, if I didn't have a stretch, it would look like that. But I have a stretch, so we have to, instead of going over 1, up 1, we're going to go over 1, up 3. Instead of going over 4, up 2, we're going to go over 4, up, let's do times 3, 6. So it's going to be much taller. Than our parent function. Vertical stretch, y'all. So let's take a look at a word problem where we're going to use graphing to help us solve. You can model the population P of Corpus Christi, Texas between the years 1970 and 2005 by the radical function P of x equals 75,000 cubed root x minus 1950, where x is the year. Using this model, in what year was the population of Corpus Christi? 275,000. So what we're going to do is we're going to type in this function into our graphing calculator. I'm choosing to use Desmos right now. So here it is. I want you to note that I'm looking at my action items here, my math calculations. This is a square root. I'm not looking for the square root. I'm looking for cubed root. Good thing we learned about how to write roots and exponents as fraction exponents. So cubed root is 1/3 power. So instead of having a cubed root out front, I'm writing x minus 1950 raised to the 1/3 power. I want to know when that is equal to 275,000. So obviously, if you look at my scale here, none of these numbers are popping up on my scale because I'm only going from -8 to +8. I want to target y in the area of 275,000. So I need to increase my window. Oh, now there's my line. That's great. I want to see my, and there's my other line. We just click. So at 1999.296, our equation is equal to 275,000. So in 1999, so let's take a little snip of this. So go ahead and recreate this little graph on your paper so you can show that. And you may also on your paper, you may want to write how we wrote this in Desmos if you are using Desmos. A graphing calculator has the cubed root already on there. So, but if you, a lot of my students use Desmos, so definitely write down this version of the equation. Okay, so let's complicate things a little bit more. What is the graph of y equals 3 minus 1/2 cubed root x minus 2? So let's go back to our graphing utility just for fun and take a peek at what the cubed root function looks like. Let me get my settings back. Okay, so a cube root function looks like a cubed function just rotated onto its side. So if I'm going to take this parent function, and so let's go ahead and draw that parent on our graph. So parent function. Looks like this. Double check to make sure I got the gist of it. Yep, that's about it. Okay, so we are going to shift that 2 units to the right. Move it 3 units because So I rewrote this function. Y equals negative 1/2 cubed root x minus 2. That 3 is technically a plus 3. So I'm going to shift it 3 units up, 2 units to the right, and then I am going to reflect it. So this negative is a reflection. The 1/2 is a vertical compress, so it's going to be flatter. And then we're going to shift it 2 units over, 3 units up. Okay, so let's reflect it first. So reflection looks like this. Then we're going to compress this down. See if I can do it here. And make it flatter. And then I'm going to shift it 2 units to the right and 3 units up. Oh. So let's take a little look to make sure we got it right. X minus 2, okay. To the 1/3 power. All right, so it goes up, has its little moment right here, and comes back down. So let's take a peek and compare it to our, we'll take a little snip of it and compare. Not too bad. Not too bad. All right. So we're using the translation properties just on roots now. Okay, so how can we rewrite y equals cubed root of 8x plus 32 minus 2 so that we can graph it using transformations? Describe the graph. So using transformations, we want it to be y equals a cubed root of x minus h plus k. So we look at this guy here. Can we factor something out of 8x plus 32? We can factor out an 8, so let's go ahead and do that. So we're starting with cubed root 8x plus 32, and it's minus 2. So we are going to factor out an 8, and we get x plus 4. Can we take the cubed root of 8?
Oh, yes.
Cubed root of 8 is 2. So I put the 2 out front. X plus 4 stays in, and then minus 2. So now I can describe the graph. It's going to have a vertical stretch up to, it's going to shift to the left 4 units, and then it's going to shift down 2 units. So by factoring out that 8, which became a 2 on the outside of the cubed root, we were able to make it in the same form so we can describe translations.